It's a great pleasure to have Pradeep Ravikumar from CMU give us the CIS talk. Now, Pradeep got his PhD from CMU. He then went on to the postdoc at UC Berkeley with Martin Wainwright. And then he took a professor position at UT Austin. And then he basically went back home to CMU to continue his research. Now, Pradeep is one of the most prolific machine learning researchers. He's a very strong contributor to the theory of machine learning methodology. His recent research interests also include things like causality, graph learning, and he's also very specialized in statistics as well. So we're really looking forward to his talk. Take it away, Pradeep.
Thanks, Volkan. So what I'm going to talk about today is what basically many people are very concerned about and I'm working on as well, which is robust learning. Here, robustness, I really mean in the adversarial robustness sense, which I'll just talk about. So this is joint work with my student Arun, who's now joined Google Research, as well as some students from Joshua Bengio's group.
Là,
So,
je l'ai. Parce que vous m'expliquez ce que c'est ça? Yes.
so adversarial ML is basically this problem where if you have your input and you're extremely confident with your input that, hey, this is a panda that I'm seeing in the image, I just have some what looks like just a very minute amount of noise, and then suddenly the neural network is extremely confident that it's a given. And so this is something that people were extremely concerned about, because if I have an autonomous car that is detecting a stop sign, then you don't want it to suddenly detect a 100 miles per hour sign by just somebody putting a sticker on top of the stop sign. But that is precisely what people showed, that a small sticker on stop signs can just confuse the neural networks. So this is obviously a big, big problem. So what do we do? So this has really kicked off a 10-year research program. So this was really, all these examples are 10 years old by now. So this kicked off this 10-year research program of how do we make sure that the neural networks we train don't have these issues. So people came up with various defense approaches. So you can think of the examples in the previous slide as attacks. And so people came up with various approaches to defend these neural networks as well. And the problem is whenever people come up with some good defense, somebody comes up with a better attack. And then somebody comes up with another defense to that attack. So far, there's been this arms race where every year, right, and with the pace that machine learning research is going on, somebody posts an archive paper on an attack. 2 months later, there's another paper on defense. So this keeps going on. And, this would be fine initially, but it's 10 years now. So, it's a little bit of a problem. And of course, people want to use these ML algorithms for things like autonomous cars. So Pittsburgh itself has 5 self-driving car startups that are unicorns. So they have more than 5 self-driving car startups, but these are the well-funded ones. Part of the reason why Pittsburgh, in case you're curious, there is CMU, of course, but my favorite explanation would be that Pittsburgh weather is adversarial. So, and Pittsburgh drivers are adversarial. So what you want is to make sure that your environment is as adversarial as possible, so that if you transport it to Sunnyvale, it's in the name, right? Sunnyvale. So if you transport it to California, it should still perform okay. But you don't want things that are driving on flat, open roads in California, transported to Pittsburgh, chaos. So that's one reason. That's one way in which you can try to get an adversarial defense, which is to try to have your training distribution be as adversarial as possible. But that still doesn't really give you any guarantees. So how do you actually do better? So one of the things people said is that, hey, if I have a single model and it's easy to attack, how about you have a collection of models, an ensemble of models? So then presumably it should be harder to attack because you now have multiple things to actually attack to make sure that you can actually fool the model. The problem, of course, is in this arms race, people said doesn't matter. So even if you have an ensemble, again, a simple ensemble would be that you don't just have a single neural network, you have multiple neural networks, and then the final prediction would be a majority vote among them. People said, too bad, we can still attack these. And in fact, what we also show is that the state-of-the-art defense can in turn be attacked. So this is one of the things we show. So what do we do, right? So again, one question you may ask is, from a theoretical standpoint, given that neural networks are so flexible, right? That is really one of the meme, that neural networks can represent whatever you throw at it, even random noise, right? So why do you expect a collection of neural networks to do any better from a theoretical standpoint? So part of the reason we were thinking that it could help is similar to boosting, right? So boosting is really one of the, many people argue, top 3 ideas in machine learning to come out of maybe the last few decades. So the high-level question in boosting is, given access to a repository of very weak classifiers, can you somehow combine them intelligently to a very, very strong classifier? So that's the high-level question. So here, if you think about neural networks as not weak classifiers in the traditional sense, but weak classifiers with respect to adversarial robustness, in the sense that they are not adversarially robust. You place stickers and stop signs and they get confused. But it's a single one that is perhaps not so ideal, but is it possible, given this collection of all possible neural networks, to have a collection of them, carefully chosen collection, that would be adversarially robust? So this question is very similar to boosting. For a while, people didn't think that boosting is possible, right? Till Rob Shapire and colleagues actually showed that it is possible. So similarly, can we do the same thing, but for adversarial robustness and the pool of neural networks? So what we essentially show is that it is possible. And the theory is basically just borrowing from the classical boosting theory. So we don't do anything too unnecessarily fancy. So what we call it is basically MR boost. So we are essentially going to give you a robust algorithm. Now there's a boosting algorithm that gives you robust models by using this margin theory. So another perspective to take on this is that this is essentially helping us systematize adversarial defense using ensembles. So just to set up the preliminaries, I have inputs that I'm going to denote by small x and then outputs small y. We can focus on the classification setting where I have finite set of labels, k labels, say. And I have n training data. And imagine that I have some pool of classifiers. Again, this need not be finite. Think of this as a set of all possible neural networks. Okay? And in adversarial learning, one of the things we have to specify is how can the adversary attack your model. And one way in which you can constrain your adversary is to say that the adversary can only perturb your input by a small amount. And so how you define this small amount essentially specifies different kinds of attacks. So a common thing is really LP norm attacks, where essentially whatever input you have, the adversary can add a small perturbation, W, which is going to be bounded in LP norm. That's it. So they are allowed to add any small input to your input. So if I have a stop sign, they are allowed to change the stop sign in some small amount, which you can think of as putting a sticker. Right? Of course, the sticker has a lot more structure. Right? It's also spatially contiguous, et cetera, et cetera. So this is actually much more flexible. It's really saying I can perturb each and every pixel of the image but its LP norm has to be bounded. So this is a common attack surface, but one could think of generalize this in any way, and our theory continues. You define basically some set of perturbations that the adversaries allow. Okay, so now let's define ensembles. So given your class of weak classifiers, if you will, whatever your pool of classifiers are, an ensemble, one way to think about it is as a distribution over your pool of classifiers. Okay, so you have some distribution Q over this pool, and then given this distribution Q, you can essentially define an ensemble which would essentially be weighted majority vote with respect to these distribution weights. So basically, if you have any classifier J, then the votes, the number of votes that it would get would be essentially by summing up the weights assigned by Q, right, which is what is given here. And so if this is for class J, if these are the votes that it gets, the output of the ensemble classifier is to output the class with the most votes, right? So that's basically how we do ensemble classification. Now, one of the things we want to define here is the notion of a margin. So what we would like is for this ensemble classifier, imagine that the input is X and the true label is Y. Okay, so the input is the stop sign and the true label is a stop sign, right? So what we would like is that this ensemble classifier to be highly confident for label Y. So that's the first term. And it should have a very low score for all the other labels. So this difference between the score it assigns to the true label and the maximum possible score for the other labels, so this is what we call margin. So again, you can think of this as the confidence of your classifier for the label Y. So what we want to focus on is the minimum margin. Okay, so this margin is again something that you defined. In my cursor has vanished, but so this margin is defined per input, and given your data set, I want to define the margin over the entire data set as the minimum margin over the entire data set. Okay, so even if basically all of the data points but one have a large margin, but there is one data point which has a small margin, my minimum margin is going to be the small margin that single data point attained. Okay, so it's very, very conservative. So what I want is that each and every point should have a high margin, right, for this minimum margin to be large. Okay, so this is the minimum margin that's on the first line. Again, you can think of the margin as how confident is this ensemble on this single data point X comma Y, and I'm looking for what is its minimum confidence over all of the data points in my data set. Now, the thing is, I don't just care about the minimum margin because I have an adversary, and the adversary is not just going to let me predict on the input X. The adversary is going to take the input X and perturb it in however which way. And so how is the adversary going to perturb it? The adversary is going to add a perturbation delta to the input X, right? So what I want is to focus on the minimum margin after the adversary has perturbed the input. Okay, so I want to take a minimum over all possible perturbations that the adversary can take, right? And so I have a minimum over the perturbations, and I have a minimum over the data points. Okay, so this is basically what we call the minimum robust margin. So our goal then, if you think of trying to find the best possible ensemble, is to find this ensemble Q, which is again a distribution over my hypothesis class, that maximizes my minimum robust margin. Okay. So again, if I expand out the definition of the minimum robust margin, we get basically the line on the bottom of the slide, right? So I have essentially tried to find an ensemble that tries to be the best as possible with respect to this margin quantity, right? So again, the margin would, what we would like the ensemble to have is be as confident as possible for the true label y, and be as have lower the confidence as much as possible for the other labels y prime, right? And I'm computing the minimum with respect to the data points and with respect to the perturbations delta. So this is our goal. Okay, so we want to find an ensemble that solves this problem, right? Now, again, this is the objective. So this is what we call a robust margin boosting game. The one question you may have is, where does boosting come in? So the interesting thing is that if you go back to the early boosting literature, it was actually formulated as a zero-sum game. It was actually specified precisely in this form, except that there is no perturbation there. So imagine that you just get rid of the min over perturbations, and then you just look at the question of maximizing the minimum margin. That was exactly what boosting was designed to do. The various algorithms like ADA boost and so on really came out of algorithms to solve the zero-sum game. So what we said is that, hey, that was 30 years ago, but now we have this, not the standard margin boosting game, but we have this robust margin boosting game. Can we still take classical ideas on how to solve zero-sum games and transport it to this specific problem? So that's exactly what we did. Okay, so you can essentially get this analog of all of the boosting algorithms that people have developed, but for this robust margin boosting game. So, so we ask many of the questions that we ask in boosting, right? So in particular, one of the things we have in boosting is, what are the conditions on your pool of classifiers so that there exists an ensemble which has perfect performance or very strong performance, okay? And so in particular, the question we ask here is, what are the necessary and sufficient conditions on the pool of classifiers so that an ensemble will be adversarially robust? And adversarially robust meaning that its robust margin would be large. So the other question you may have is there some other approach that can basically give us better adversarially robust ensembles? Okay. So in other words, are there other approaches that don't just involve this kind of solving this boosting game that would give us better adversarial robustness? So we are able to answer both of these questions, again, by drawing from the very classical boosting literature, which in turn, right, is actually drawn from the game theory literature. So what we, in our case, is what we have to do is define an augmented data set. So in our data set, we have inputs X and outputs Y, right? But we have this augmented data set where we also add in two additional ingredients. We add in labels Y prime that are wrong, and we add in the perturbations delta that the adversary is allowed to do. Okay, so for any input and its corresponding true label X comma Y, essentially the Y prime is just what are the other labels, and delta is the key thing, really. That's where we are augmenting. Essentially, we are augmenting the test inputs with all possible perturbations to the test input. Okay, so what is our weak robustness condition? So a weak robustness condition is essentially the counterpart of the weak learning condition for boosting. So what we essentially say here is that for any distribution over this augmented data set, there exists some classifier in your pool whose adversarial robustness is slightly better than random. By that, I mean that its adversarial robustness is slightly better than the adversarial robustness of a completely random classifier. Okay, so again, in the context of binary classification, what it's saying is that if if I have essentially any distribution over the set of permutations, okay, so this is in fact slightly, you may think of this as stochastic perturbations rather than just as a point mass at a single perturbation, but this is more general, right? This includes a point mass on a single perturbation delta, but here the adversary has the option of having a distribution over possible permutations. Okay, so what it's saying is that then if I look at the expected accuracy of any classifier, what it's saying is that there exists some neural network whose accuracy is going to be better than random. That's it. That's all I'm saying. So I don't want to necessarily say that this is a trivial condition, right? What it would mean is that, let's say I have stop signs and I have to predict whether it's a stop sign or non-stop sign. What I'm saying is that no matter how I specify a distribution over permutations, there exists some neural network that can perform better than random guessing. Okay? So I don't also want to say that this is too stringent, because there could be some neural networks, or perhaps most neural networks, which could be attacked by a specific attack, right? So if I create a sticker, let's say, right, it could maybe fool some neural networks or maybe most neural networks. All this is saying is that there exists some neural network that's not going to be fooled by the sticker. Okay, so that's what this is saying. So what we show is that this weak robustness condition that we just defined is both necessary and sufficient for the robust margin gain to yield an adversarially robust ensemble. So in other words, if this weak condition holds, and this is a condition on your pool of classifiers, right? What it's saying is that if your pool of classifiers satisfies that condition, then there exists some ensemble that is adversarially robust. Okay. The second theorem that we show is that there exists no other approach that can yield an adversarially robust ensemble under weaker conditions than actually solving this robust margin boosting game. So that's your best bet. If you want a robust ensemble, you really have multiple defenses in the sense of multiple training algorithms. What we are saying is that solving this margin boosting game is your best bet. In what sense? In the sense that we would require the weakest condition on the pool of classifiers. So this is again something we can show. Okay, so that's basically the thing. Okay, so if solving the robust margin boosting game is our best bet, then let's go ahead and solve the robust margin boosting game. And so here again, what we do is just use really classical game theoretic tools, but with some modern fixes on those. And so that yields an algorithm we call MR boost. And so the algorithm is here. So this basically involves something we call the pairwise margin loss. That's on the right side of the slide. So what it's looking at is basically a pairwise loss. So your H is your classifier, right? And I can look at, given a particular test input X and its true label Y, I can check, is it making a mistake? Right? And so what I can contrast it is it making a mistake on the true label Y, and subtracting that from whether it is making a mistake with respect to an incorrect label Y prime. Okay, so we call this a pairwise margin loss. So instead of comparing the accuracy, which is a probability of getting the label correct, right, versus not, so this is just looking at a particular instance of the true label and an incorrect label. And what we do is basically in each round of boosting, we try to learn a classifier that basically minimizes this expected pairwise margin loss. Okay. And just like in boosting, if you remember boosting, right, what do we do in each round of boosting? We take our data set and we reweight the data points, right? So we do the same thing here, except that instead of just reweighting your data points, we now reweight the augmented data points. We now have not only the data points x comma y, but we also have the perturbations delta. So in each round, we also carry around a distribution over the perturbations.
So from what I understand, you skip the optimization over the perturbations.
That's
so
right.
You basically create a data set with possible perturbations.
That's right.
Then basically run this min-max problem where the distribution is optimized over the classifiers. And you also determine the classifiers as a way of minimizing over the also possible perturbations.
That's right.
Okay, so there's no joint optimization. Somebody is not necessarily adversarially also figuring out what directions they should choose. The directions are fixed. The perturbation directions are fixed.
So there is a distribution over them.
Okay, but you're learning the distribution over them as opposed to also learning the perturbations per se.
So that's actually a very good question. So let me go to the margin boosting game. Where do we have it here? So the usual way in which we do adversarial training is where for any x comma y, I try to find the perturbation delta that can attack it the most.
So it's fixed and learned here.
So instead of minimizing over the perturbations this way, what you can think of as a slightly more flexible thing is it's minimizing over distributions over permutations. And effectively, that's what that margin boosting game is doing. You can think of this as us learning a distribution over permutations that can maximally attack this ensemble.
Okay, so PT is being learned.
Yes. So we are actually learning a distribution over permutations that can maximally attack. So this is very similar to boosting, where the reweighting that we do in classical boosting, again, in classical boosting, we want to boost weak classifiers whose accuracy is slightly better than random to something whose an ensemble whose accuracy is close to 100%. And the way we do that is by learning a distribution or the data points that is as bad as possible for this ensemble. Here we do the same thing.
So in this case, P's are infinite dimensional problems. So these are infinite dimensional.
That's right. That's right. So this P is a distribution of permutations, which is a little bit of a hassle because, again, this delta, again, it's drawn from a compact set, right? So you have an LP ball and the radius of the ball is at most epsilon, but it's still an infinite set. And what we have is this distribution over data points and perturbations given precisely by this. So in practice, obviously, we sample and have a finite set of particles rather than explicitly storing this distribution. But that's basically this thing. So in each round, you can think of this as basically, let's see if I, yeah. So in contrast to standard adversarial training, which really tries to, at each step, tries to get specific perturbations that are the most harmful for your neural network or whatever your model may be. Here it has a distribution over permutations, perturbations. So though the thing is that you can think of these as very, very close to the standard adversarial training. So one way of rewriting this distribution, again, I don't know the cursor here, apologies, is as in the bottom of the slide here, where I have essentially, you can think of as in each step, it's trying to learn the worst possible distribution for your ensemble. Okay. But what does worst possible mean? it means that it'll try to maximize the loss that you will suffer, right? And here the loss is with respect to this pairwise margin loss. Okay, so if I were to just maximize the first term, right? Again, because it's linear in P prime, this would just be a standard adversarial attack where I would try to find essentially a single perturbation delta that attacks my neural network, right? But what I have here is this additional entropy term. Basically what I encourage is a little bit of an entropy. So rather than having a point mass, I want it to be have this entropic regularization. And so this is what we are essentially doing. It's kind of, you can think of it as a regularized adversarial attack. Again, this wouldn't be surprising for those of you working on algorithms to solve min-max games, but this is basically, so for those of you working on online learning, this may again look a little bit familiar, right? And this is again because a standard way to solve min-max games is by reduction to online learning. So that's also for those of you who may suddenly be curious as to why does this look so much like a online learning algorithm. That's basically why. So that's basically what our algorithm is. It's basically just a modest take, a variant of how we usually do adversarial training. But in contrast to the standard way of doing adversarial training, where we don't have a lot of guarantees, here we actually have very strong guarantees. If you just do this T steps, so in other words, you learn T neural networks or whatever models you may have, then the ensemble that you would learn, it would be d over square root T close to the solution of your robust margin boosting game. Moreover, the mixture distribution, or basically the perturbation distributions defined here, this actually concentrates around the basically the most difficult adversarial examples of your ensemble. Okay, so we are basically, again, those of you who are working on min-max games, this is basically, we are getting closer and closer to the mixed Nash equilibrium of our robust margin boosting game. That's what we are saying. Again, these are relatively standard things by now. I was just found out that Volkan has a paper on using some of these ideas for solving GANs, where also you have a min-max game. So that was basically the thing. And there's one additional ingredient that I wanted to bring up, which is that some of you may think training a single neural network is painful enough, right? You're not going to get me to train an ensemble, which is fair enough. So if you are going to train a single neural network and you want to have adversarial defense, so what that means is that you have some way of training your neural network. What we would recommend is that instead of your standard cross-entropy loss, okay, which is basically, again, what is a cross-entropy loss? That's given in this expression, right? So again, if your model is G, again, it's just a mapping from the input X to your output space. So the cross-entropy loss compares, so this is typically used in classification where your output space is finite. It's the set of labels, set of classes. And this is basically one common laws used to train neural networks or most models, right? So for instance, if this G is a linear function, then this would just be logistic log likelihood, right? So this is one of the advantages of this, is that this is a very, very useful surrogate for the 0-1 classification loss, which just checks, is G of X the same as Y or not, right? If it is not, you get a loss of 1. If it's right, you get a loss of 0. This is a step function, if you think of it as a product of its X and Y, but it's not really a nice, well-behaved function. But whereas this would be a nice and smooth function, and if G is convex, then the cross-entropy loss would also be convex. So this has nice properties. But what we would recommend is that you use essentially, instead of the 0-1 loss, you use this pairwise margin loss that is coming out of a robust margin boosting game, right? Where again, the pairwise margin loss I had introduced before, right? Motivated by that, you can essentially think of as a margin cross entropy loss, okay? Where essentially you have a difference between two cross entropies. So you check the cross entropy loss with respect to the true label, and how much do you differ from the cross entropy loss with respect to the incorrect label. So you have these difference of cross entropies. Of course, this would not have some of the nice properties of cross entropy in the sense that if G is convex, then the overall loss function would be convex. But you're training neural networks, so nothing is convex anyway, right? So what does a difference of two cross entropies do to you anyway? So that's basically what we do. Now, the thing is, for binary classification, this is actually turns out to be convex if G is convex, in the sense that this would just be a scaling of your standard cross entropy loss. Okay, so you're not really doing anything for binary classification. I should mention that, right? But because Y prime is basically just the other label, right? So you're not really doing anything. But for multi-class classification, this does yield a completely different loss. And what we basically show is that you can just use your favorite adversarial defense strategy, just use that strategy with respect to the MCE loss rather than the CE loss, which is what is usually done, and you get much, much better adversarial defense. Okay, so here is basically our results. So for instance, if you have really the standard adversarial training, which again goes back to the earliest Alex Madry paper, so what we have are basically three data sets, what, SVHN, and then a bunch of CFAR data sets. Let's just look at basically these numbers. Let me actually use my cursor here. So what we can see is that adversarial training, again, there are much better defenses that we have right now. But you can see that, again, so here, what are these columns? So clean is basically where there is no adversary perturbing a test data set. And this is where you have perturbations that are adversarially chosen. So what you can see is that adversarial training is getting some performance, right? And just by adding this MCE loss, you're getting an improvement in adversarial performance. Okay, and this is basically the case across data sets. Okay, so you can see again here on CFAR 10, what you can see is the adversarial training gives us 50.95, and here you get, so again, the improvements are not totally mind-blowing, but here, remember that we are just changing the loss function slightly, motivated by a robust margin boosting game. And this is basically the case even for other adversarial defenses. Okay, so these are all much more recent adversarial defenses compared to adversarial training. So they have better performance across data sets, though not always, right? So this is really a hard problem. What we are seeing is that just by adding, just keeping your adversarial defense strategy, but just adding this MCE loss gives you better performance. So this is one thing I would say. Even if you don't care about ensembles, use this MCE loss, which is again motivated by the robust margin boosting game.
This is very impressive because it's very difficult to beat the state of the art numbers.
Yeah.
So swapping the cost function. Wow.
So so this was surprising to us that
It's quite impressive.
Yeah. And if
even 1% improvement.
Right. Yeah.
You're at the really thin edge.
Yeah. You can see that again. This was close to 10 years ago, right? So people are improving ever so slightly on many of these benchmarks, but you get the boost. And of course, if you actually do this boosting, what we find is that in each boosting iteration, you actually perform better and better. what we have is basically, so again, in boosting, if you're training neural networks, we tried a couple of things where in the next boosting iteration, you can initialize the neural network of the next, in the next boosting iteration with the parameters of the earlier boosting iteration. If you're thinking adversarially, you might think that this is bad. But if you're thinking in terms of optimization, maybe you think this is great. So we just tried both this persistent initialization and random initialization, just see what the difference in performance is going to be. And what we found is that the persistent initialization actually helped. But this could just be an optimization artifact. But what we found is that this did help. So let's just look at, for instance, instead of the clean column, let's just look at the adversarial performance column. So we can see that so raw boost is another simpler boosting algorithm that we used. So this is really our algorithm, MR boost. And what we are seeing is that, let's just look at these numbers. You can see that they slowly improve, right? So this says that as you add more and more ensembles, you are improving your adversarial defense. And this is also suggesting, by comparing these two numbers, that persistent initialization is actually helpful. Modestly, but it's helpful. So again, this is with respect to adversarial performance, right? Training time persistent initialization is much, much faster. So this is basically best of both worlds. So that's basically what I wanted to talk about. We were focusing on how to get ensembles that are adversarially robust. And we provided basically the optimal approach, right? And the reason we're calling it optimal was basically because of the second theorem that said that if you do anything else, then you are going to require stronger conditions on your pool of classifiers. So solving the robust margin boosting game is the best bet. So again, the require solving is zero-sum game, which we punt a little bit in the sense that, not punt really, but the reason we are getting an ensemble is that if you solve the zero-sum game exactly, and I hear that Volkan has some exciting algorithms to exactly solve the zero-sum game, you don't need an ensemble. Okay, so this is basically one thing where it is possible to solve the zero-sum game and get a single neural network that solves the robust margin boosting game, which could maybe get you a single neural network that is very good. But if you think again in terms of a zero-sum game, instead of getting the Nash equilibrium, if I get a mixed Nash equilibrium, right, where you essentially have a distribution. So instead of just, so you have these mixed strategies or essentially a distribution over your actions. So here actions are models. So you get a distribution over models. That's the output of our mixed Nash equilibrium algorithm. And again, we just use a standard algorithm, right? So that's basically gets us these ensembles with strong guarantees. And the other thing that we would like to emphasize is this novel surrogate loss for multi-class classification that we call margin cross-entropy loss, that especially in this context of adversarial robustness, if you care about the robust margin, then just use this, which is essentially a modest, if it's binary classification, it's the same, just scaled. But if it's multi-class classification, which most of our problems are, this is a different loss. And it gives you a big boost, not big, but reasonable boost. So that's basically it. And so this is our paper. Thank you.
So to be honest with you, I'm not sure.
I can repeat.
Speak loud. That should be.
I can repeat the question.
So I have one short main question and another one. So my first question is on this difference of cross-entropy loss. I guess one thing that confuses me is if you return to the definition. So you've got g of x at y, and then you have a log normalizer that basically doesn't depend on y. So if you take the difference of two such terms, don't you just get gx at y minus gx at y prime? with a one normalizer that disappears, cancels out. So it's just the difference of the scores, you know, so it's just a hinge loss. Or maybe there's something that I'm missing.
That's actually a good point. That's yeah, that's actually a good point. So you would get essentially a difference between the scores for y and y prime. That's right.
It looks like a hinge loss, and somehow it's coherent with what you were saying, that you want to be robust to perturbations of the network.
That's right. That's right. Right. So this would basically be so this won't be exactly the hinge loss, because again you have this y and y prime, and you're taking an average over those because of the way you define this pairwise margin loss. So you try to let's see if I can go here.
It's average over a distribution, which is going to put more weights on the worst possible y prime.
That's right. So it is kind of
Soft hinge loss.
It's a soft hinge loss. I think that's a great way to look at it. Yeah.
Then my second question is about your necessary and sufficient condition.
Mm-hmm.
And so maybe there's I don't interpret it well, but so if I interpret it well, you're saying that you require that there exists a binary classifier, which is such that for any distribution that I put on S prime, it's able to classify it with some more than 50%.
It's with the quantifier switched. Given any distribution, there exists one. So we are not saying that there.
Then somehow in the set S prime, you're allowing E to choose delta, which so B of epsilon is the ball, it's not the sphere.
That's it. Yeah.
So you're allowing that to take delta, which can be arbitrarily small, and to choose a different label y prime than the true label y in the original data set. Is that right?
So y prime is a wrong label. So that's the restriction here. So you just have, so think of this as I'm only computing the margin with respect to the incorrect labels. So it's so I have the true label and an incorrect label, and I can look at the difference of the margins, and I'm taking an average over the incorrect labels, and the weighting I would have in that average. So essentially, I can essentially only look at the difference with respect to the worst possible mistake. So this is what SVMs do, for instance. Here, you're computing an average.
So what you're saying is that, okay, so I'm allowed to choose which label the amalgam to be computed with.
Yes.
And I want to be robust to any possible alternative.
Any possible alternative, exactly. Right, right.
Yeah. I think you actually made a good point. The cost function that they're proposing is taking the original one that they have the theory for and smoothing it. And then the smoothed version, because it's like a mini maxi game, it gives you an advantage for the outer optimization. And it's nice to see that it actually does, because the gains in the state-of-the-art results is so slim that just changing it and giving that advantage gives you a 1% boost, or I saw 2% boost.
Yeah.
They're pretty impressive.
Yeah.
It's very, very interesting.
So actually, regarding those results, it seems that you are trading off some of the clean accuracy when looking at the tables, similar to what trades would do. So have you seen if you increase the regularization parameters you have in trades, you could trade off more of the clean accuracy with cost accuracy? What's the comparison?
Right.
This is trades used when trying to maximize the robust accuracy or what?
Yeah. So that's actually a good point. So basically, the question was, if you look at the clean accuracy here, then in certain cases, the clean accuracy without the loss substitution is better. So in some cases, or actually, in many cases, the clean accuracy is also better. So you can see basically this actually has better. But there are cases, like on CIFAR 10, where the clean accuracy is slightly better. I think it's an interesting question that if there are tuning parameters that allow us to trade off clean versus adversarial performance, could we kind of get it as well? But again, here the goal is to get good adversarial performance. Many of these state-of-the-art methods, that is their goal. They don't necessarily try to trade it off. But that is an interesting question, which is, can we, so because I think ultimately, so to riff on that question a little bit, ultimately we train these robust models on training data and then evaluate it on test data, right? Is it the case that by being too focused on adversarial robustness in the training data, it doesn't generalize to the test data? So that maybe by pulling it back a little bit so that your clean accuracy is better, you get better adversarial performance on the test data. So basically, that would be one extension of your question. That's a good question. I don't have an answer to that, but we don't exactly see that the clean performance always worsens. Sometimes it increases, sometimes it decreases.
In certain formulation to learn neural networks, literature on putting a distribution over the neurons themselves, right? So I mean, if you have a one hidden layer, you can model the learning as learning after distribution over neuron parameters. I'm just wondering if somehow this idea of boosting could be used directly inside of the neural network architecture. So instead of boosting different neural networks, basically use this kind of formulation to learn the distribution over neurons themselves.
That's actually a fantastic question. So we actually had a paper last year or so where we asked the question whether we can actually learn these compositional models by drawing from boosting. So it's it's an old idea. So Joshua Bengio had this, I think, again, 2005 or so, where essentially it's layer-wise training. But you do layer-wise training, that's what people were doing, but that kind of got thrown out because people said end-to-end training is so much better. It was able to get better performance. So what we did was, so again, Joshua Bengio was focused on layer-wise training. So what we then said was, last year, if you connect it to boosting, then can you do this systematically and better? Can you learn these compositional models better? And so we basically did, but it was still slightly worse than end-to-end training. But one question would be, can you combine that with this and get basically an adversarial ensemble, but not of entire neural networks, but of so basically, just as a one-line summary of that earlier work, if you think of a ResNet, then it's basically an ensemble, right? Where you can think of each residual layer that you're training, and then you're adding it to what you had till the previous layer. So you have an ensemble anyway. And so what we said is that let's learn a ResNet using boosting. That was basically our paper, where there were certain things you needed to do systematically. So there you're training essentially each layer using boosting. But now if you also add in this element, where so one way to think about it is that your pool of classifiers is not just gigantic neural networks, but really much smaller ones. And your things that are only perhaps a single layer on top of other things that were trained before. That's a very interesting question. That's what looking into.
Other questions from the audience? Any questions from Zoom? All right. If not, let's thank the speaker and CIS.